Okay, finally, there you go. Good morning again, everyone. And it's nice to be with you again for this week's discussion. This would be the last module for Math 174, and hopefully I can finish its coverage today so that you will be prepared for the laboratory exercise on Monday about the contents of Module 11. It's not that long. I'll try to finish it today and focus more on the implementation nitty-gritty of this method. We will be talking about Monte Carlo methods. I did not include in the discussion the theory or much of the theory behind Monte Carlo simulations. So medyo focus tayo dun sa implementation ng method. There are some commentaries I made about the methods, its significance, its advantages over the quadrature rules that we discussed last time. But probably I'll be leaving a good chunk of it as a reading assignment for you para matapos natin yung implementation phase or i-discuss yung implementation phase ng Monte Carlo simulations today. Now, before I proceed, since the semester is almost done, we will have the last problem or the second problem set next week. We will also have a final project, but it will be due during the finals week next year. So during the first week back from the Christmas break, we will have the final project. In preparation for it, I encourage you guys to talk among yourselves and form your groups. I decided that there could be at most 4 members for a certain project. So pwedeng isa, dalawa, tatlo, or apat kayong mag-work together for a single project. More details about the project will be out next week. I'll be preparing a document to give you a detailed explanation and guidelines for that project. Pero yun nga, unahin natin yung paghahanap ng grouping. So you can form groups of up to 4 members. Bahala na kayo kung ilan, basta wag lalampas ng apat. Free Feel free to form the group yourselves. It could be someone from your own section or your own lab section. It could be from another lab section. It could even be from another lecture section. I don't care too much about that. Basta kaklase nyo sa 174, either section B or section V, that's perfectly fine with me. For those who want to work in a group but don't have specific group mates in mind, you can fill up the Google forms or the Google form that I sent via the chat. There's a link in our chat, in our meeting chat today. Paki-click na lang yan and please fill it up. Perhaps I'll form the groupings. Maybe I'll give you 1 week, siguro by Thursday next week. Hopefully, everybody who wants to be grouped or who wants to be assigned to a group already signed the form by Thursday next week para mailabas ko rin yung grouping by Friday next week. So paki-fill up na lang. I also sent it as an announcement in Canvas. So yeah, check it out, guys. And again, please fill it up before Thursday next week. And then also, I apologize, I forgot to upload yung recording ng meeting natin about integration anomalies last time. For those who are not member of the teams, you might had a difficult time accessing it. I apologize for the inconvenience, but that's probably the perk of being a member of the team. So meron silang access right away to the video recordings, even if I forgot to upload it in YouTube or in Canvas. Okay. So with that out of the way, let's start talking about Module 11. Okay. And as I've mentioned, this is the last module for the course. We'll cover it today. Hopefully matapos ko siya in preparation for your laboratory synchronous session on the 13th. That's on Monday. And the deadline for the exercise attached to Module 11 would be on December 13, right before midnight. I uploaded Module 11 late last night, but there's no laboratory exercise yet. I asked the lab instructor assigned to finalize it probably within the day or di pala within the day. I gave him until Saturday to upload or to give me the draft lab exercise. And once I get it, I will upload it in the assignments tab in Canvas, and I will edit the copy of Module 11 in our module section in Canvas to include Lab Exercise 7. Okay, so but for now, just chill there and let's talk about how Monte Carlo integration is implemented. Okay, as an alternative to the numerical integration schemes that we talked about last time. So what's the problem about the numerical integration schemes that we have developed last time? Well, it's not much of a big problem, but they are what we call deterministic methods. That means if you're given, for instance, in the Newton codes quadratures, if you're given a specific set of data points, all right, I mean exabytes comma f of exabytes. So if you're given that distinct set of data, by the unisolvence theorem, there is exactly one and only one interpolating polynomial that will pass through all of those data points. So dahil isa lamang yung interpolating polynomial na dadaan dun sa data points mo, yung Newton-Cotes quadrature rule, which is derived by integrating that interpolating polynomial instead of a continuous function, all right, will give us one unique approximate for the integral. All right? So kaya siya deterministic. Input nyo ay specific abscissas and function values. Interpolate mo siya, isa lang yung interpolating polynomial. So pag in-integrate natin yung interpolating polynomial na yun, we will get one unique number. And that unique number is the approximate from the Newton-Cotes quadrature rule for the integral that we desire. Okay? Now, on the other hand, if you look at the Gauss-Legendre quadrature rule, kapag ka meron kang specific choice of degree of precision, say gusto mong degree of precision ay 2n minus 1, so meron ka lang isang unique set of abscissas and weights na mako-compute para dun sa Gauss-Legendre quadrature rule. That will give us exactly one approximate for the actual integral. So itong mga fixed parameters na to, they determine a fixed approximate for this quadrature rules. Now, Monte Carlo simulation is actually a more probabilistic estimation procedure for the definite integral. So ibig sabihin, kahit pag meron kang data point, so meron kang function, given function, tapos sinabi mo, okay, I'm going to use 1,000 points or I'm going to use 1,000,000 points para makapag-approximate ng integral. Sa isang run ng sa dalawang runs ng Monte Carlo simulation, posibleng dalawang magkaibang approximates yung makuha mo. Kasi nga, probabilistic siya, nakadepende sa draw mo ng random numbers yung makukuha mong result from a Monte Carlo simulation. So at the end of the day, when you do the exercise, we might have different answers, all right? And depending on the number of points, the accuracy of these estimates that we get might range from a good, say, less than 5% to as bad as about 200 or 350%. So yun nga lang yung problema sa Monte Carlo simulation. So it's probabilistic, meaning it's non-deterministic. And second, it's a hit and miss method. Siya hit and miss. So it's either we get a nice approximate or we don't. Now we will discuss what will increase the chances or what can increase our chances of getting a good approximate to the integral. And you will see that it is not too much of a big price to pay compared to doing Newton codes or Gauss-Legendre quadrature rules. Ang problema natin sa Newton codes kasi ay problema natin pag gusto nating maraming points ang gamitan, we will be subject to the Runge phenomenon. If we will use composite Newton codes quadrature rules, medyo maraming operations ang kailangan natin gawin. We will do function evaluations, we will sum them up, we will compute associated weights for each of the abscissas or the given data points. Medyo matrabaho pag maraming points ang kailangan. At matrabaho rin siya, or actually subject nga siya sa Runge phenomenon. Sa Gauss-Legendre quadrature rules naman, hindi ganun ka-adaptive yung method. Pag nagbago yung isip mo na ganito lang yung degree of precision na gusto kong gamitin sa bagong simulation, you have to redo everything from scratch. And computing the abscissas and the weights for the Gauss-Legendre quadrature rule is very expensive, especially for large values of n. All right? Because if you will use, say, n points, so imagine, gagamit ka ng 1,000 points para sa Gauss-Legendre quadrature rule, kailangan mag-solve ka ng 2,000 by 2,000 nonlinear system. Napakalaking nonlinear system na yon, and I guess you guys experienced the difficulty of solving this big nonlinear systems using your computers. Medyo yung iba nahirapan na daw dun sa 10 by 10, understandably so. Especially for MATLAB, it is not designed for symbolic calculations. Wolfram Mathematica will work, but it already took about 10 minutes para ma-solve yung 10 by 10 system. So imagine if you will have a 2000 by 2000 system, the running time will definitely be exponential, or it will grow exponential. So medyo malaki yung problema. Sa Monte Carlo simulation, kakaunti yung computations na kailangan. I mean, hindi ganun ka-complex yung mga operations na kailangan natin gamitin. Marami sila kasi gusto nating mas maraming points yung gamitin, but each of the calculations is not that expensive. So madali siyang i-implement. Pangalawa, napakadali lamang nung teorya sa likod ng Monte Carlo simulations. We said it's a hit and miss method, and it is actually, hit or miss method. Tapos, minor calculations lang yung kailangan, all right? And then, ang idea sa kanya ay actually isa tong method na na-develop ni John von Neumann and Stanislaw Ulam during the Second World War. And they used several experiments in order to simulate uncertain conditions. So, kaya yung Monte Carlo simulation ay hindi lamang siya applicable sa integration, ginagamit din siya sa maraming mathematical experiments or numerical simulations na ipa-perform mo yung same simulations, say 1,000 number of times using different subsets of your data points, and then i-average out mo lang yung mga results ng simulations mo. All right? So medyo repetitive siya. Tapos yun nga, it's a make or break method. Posibleng napakaganda nung makuha mo or hindi. Kaya ang tawag sa kanya ay Monte Carlo simulation. It was named after the town Monte Carlo in Monaco, which is actually known for its casino. So parang sugal yung pagpa-perform ng Monte Carlo simulation. But in math or in numerical analysis in general, we'll try to see ano yung limits ng Monte Carlo integration at ano yung pwede natin gawin para dun tayo pumunta sa hit side at hindi dun sa miss side. Okay? So here I outlined some of the nice properties of the Monte Carlo simulation, some of its advantages. First, it is very simple and easy to implement. Okay, when I say easy, madaling i-program. Pero yung implementation, medyo maraming calculations ang kailangan gawin, but we will not do them. Yung computers natin ang gagawa ng napakaraming calculations na yon. All right. So basically, it is based on the law of large numbers or the central limit theorem in statistics, which says na kapag kang isang experiment, ginawa mo with a sufficiently large number of times, then yung results mo will conform to the expected value. All right. So halimbawa, if you do, we know that theoretically, in a coin toss, the probability of getting ahead is 50%. All right. Now, the law of large numbers says, or intuitively says, if you flip the coin, say, 1,000 times, all right, then the number of heads that will result in the toss will be somewhere around 500. Okay, about half. If you flip it 1,000,000 times, then the result will be much closer to 50%. So parang if you want to get the expected value of the experiment, then perform the experiment a large number of times. So yun lang yung sinasabi ng Monte Carlo simulation. So makikita nyo mamaya yung Monte Carlo simulation will results from a drawing of sample points. So the law of large numbers says if we want to get a good approximate for the integral using random draws of data, then perform a lot of draws, all right, para maganda yung makuha mong approximation. Okay, that makes it simple and easy to implement because once you have a drawing of the sample points, then you're done. You just get the sum, take the average, and so on. Then you'll get the approximate. Okay. Second is that the method doesn't suffer from instabilities caused by non-smooth integrands. Okay? Hindi rin to na-hamper o hindi rin siya na-apektuhan ng complexity ng integrand. When I say complexity of the integrand, I'm referring to the difficulty of finding the antiderivative of the integrand. Pwede rin naman sabihin natin na hindi siya gano'n naapektuhan nung number of operations involved in computing the function value of the integrand. Pero it's not, but here I meant more of computing the antiderivative. Kasi yung computations medyo maapektuhan din siya kasi every time nagpa-function evaluation tayo. But function evaluation is a good price to pay rather than solving a system of nonlinear equations, which is the case for your Gaussian quadratures, or solving for the integral of a long Lagrange basis polynomial for the case of Newton-Cotes quadrature rules. Okay. Now, the third bullet says that the uh, the um, the accuracy of the method doesn't depend on the dimensionality of the problem. So, ibig sabihin kung yung problem nyo, nag-integrate kayo in one dimension, usual integral over R, over an interval AB, then, syempre, alam natin yung sa Newton codes o kaya sa Gaussian quadrature, lagi silang depende dun sa sampling o dun sa step size na ginagamit, right? Kaya nga meron tayong order of convergence and so on. Okay. Now, kapag ka pumunta ka na sa, say, 2D, nag-approximate ka na ng double integral, all right? So, if we wish to use endpoints, all right? So, medyo lumalaki yung number of points na kailangan natin gamitin. Kung gusto mong step size ay 1/2, halimbawa, tapos ang interval AB natin ay 0, 1. Kung one dimension lang yung integral, meron lamang tayong dalawang subdivision points, or actually, dalawang intervals at tatlong subdivision points, A plus B over 2, at saka B, all right? Yung midpoint, saka yung dalawang endpoints. Pero kapag ginamit mo yung same na step size 1/2, pero sa double integral, so meron tayong tatlong points sa interval AB, all right? So that would be A, their midpoint, and B. Tapos um, meron din tatlong boundary points para dun sa interval CD, dun sa kabilang axis, dun sa y-axis. So, ibig sabihin, meron tayong a total of 3 times 3, meron tayong 9 subdivision points. So, imagine the lift. Imagine the reach from using only 3 points kapag one-dimensional yung integral to using 9 points using a two-dimensional, or in approximating a two-dimensional integral. So, and then doon nagdidepende. So, yung number of points natin ay lumalaki masyado kapag lumalaki yung dimension ng problem. Tapos remember, nakadepende yung convergence ng mga quadrature rules natin sa step size na ginagamit. So, ibig sabihin, if you retain the same step size, your number of points increases exponentially, or as a power of the dimension. So, medyo nagiging komplikado computationally yung method. Or conversely, if you want to get a certain accuracy, may makocompute ka na step size h na optimal para dun sa multidimensional integral. Pero yung step size na yon ay magta-translate into a smaller step size pag kinonsider mo na yung subdivision sa bawat axis dun sa multidimensional integral. So masyadong malaki yung epekto dimension ng problem doon sa complexity at sa accuracy ng quadrature rules natin. Kasi nga, halimbawa sa 3D, three-dimensional integral, i-discretize mo yung x-axis, yung y-axis, yung z-axis. Tapos kung ilang points sa bawat axis, kukunin natin yung product ng tatlong number of points sa bawat axis, yun yung number of points na kailangan natin. So makikita niyo napakalaki nagiging epekto ng dimensionality ng problem. Pero sa Monte Carlo simulations, hindi siya naapektuhan ng dimension ng problem. So the error estimate sa Monte Carlo simulation ay 1 over square root of n sa kahit na anong dimension ng integral. So if you're integrating over a subset of r to the d, so d-dimensional yung problem, yung proportionality constant dun sa error ay laging Oh, sorry, yung error estimate ay laging proportional sa 1 over square root of n. So, ibig sabihin, hindi nagma-matter kung ilan yung dimension. So, pwede kang pumili, halimbawa, meron kang two-dimensional object, pwede kang pumili doon ng, say, 3,000 random points. Hindi mo na kailangang i-discretize yung x at saka yung y-axis, alright? Because the step size, there's no concept of step size in Monte Carlo simulation. Tapos, hindi siya nakaka-apekto dun sa error estimate. Sure tayo na kahit anong dimension ng problem, if be it 1, 2, 3, 4, 5, or 6 dimensional, laging yung error estimate ay 1 over root n. Okay? Now, to illustrate kung bakit nagkakaganito, tingnan natin yung Simpson's rule. Okay? Yung Simpson's rule ay order of convergence 4. So that means the proportional, the error using Simpson's rule is always proportional to h to the 4. Right? So, ibig sabihin, yung error sa composite Simpson's rule ay nagko-converge kay 0 kasing bilis ng pagko-converge ni h to the 4th, where h is the optimal step size. Alright? Tapos, kay Monte Carlo simulation, kahit sa unit interval, so the same Simpson's rule, the same integration interval as sa Simpson's rule, yung error niya lagi ay proportional sa 1 over square root of n, where n is the number of subintervals used. Okay? So halimbawa, tingnan natin yung mangyayari sa higher dimensions. So halimbawa, gagamit ako ng n subintervals, okay, sa bawat coordinate axis. Halimbawa, nag-i-integrate tayo over d dimensions. So yung integral natin ay iterated, meron kang d parts, alright? So sa composite Simpson's rule, extended d-dimensional plane, alright? So halimbawa, 3-dimensional. So, kailangan i-discretize mo yung x-axis, i-discretize mo yung y-axis, i-discretize natin yung z-axis. Yan yung kailangan nating unang gawin. Alright? And then, if we will use n subintervals in each coordinate axis, then that means we will end up using n to the power d number of points. Right? Kasi sa bawat dimension, gagamit tayo ng n subdivision points. So meron tayong d dimension. So there would be a total of n to the power d na data points na gagamitin para sa composite Simpson's rule. Let's call n to the power d capital N. Right? Now, tingnan natin ano yung minimum dimension para yung Monte Carlo simulation ay kasing ganda na nung Simpson's rule. Alright? So, alam natin na yung error sa composite Simpson's rule ay proportional sa sa h to the 4th. Okay? Now, what is h? That would be the step size. Alright? So, ang step size natin ay 1 over n. Kasi sa bawat coordinate axis, gumamit tayo ng n subintervals. So, ibig sabihin, sa bawat coordinate axis, 1 over n yung length ng bawat subinterval. So, yun yung step size. So, yung h to the 4th, o yung h ay equal kay 1 over n. So, yung h to the 4th equal kay 1 over n to the 4th. Pero again, with our convention earlier, sabi natin si capital N siya yung tawagin nating n to the power d. So yung n to the 4th, pwede nating isulat as capital N raised to the 4 over d. Right? So ito yung proportionality constant dun sa hindi pala siya yung proportionality constant. Yung error sa composite Simpson's rule ay 1 over capital N to the 4d. So nakikita nyo yung dependence niya sa sa dimension ng problem, kung ilang dimensions yung ini-integrate natin. All right? And let's see. When d is large, 4 over d is small. All right? 4 over d is small, that means n to the power 4 over d is small. 1 over small number, that will be a large number. So makikita nyo kapag ka lumalaki yung dimension, lumalaki rin yung error dun sa Simpson's rule. Okay? Now, if we will compare this strategy with a Monte Carlo simulation, and we said without proof that the error in the Monte Carlo simulation is proportional to 1 over the square root of n. Tingnan natin ilang dimensions para maging on pace na o maging nasa parehas na level yung accuracy ng composite Simpson's rule at saka ng Monte Carlo simulation. Alright? So itong error sa Simpson's rule, i-equate ko lang siya sa error proportionality constant ng Monte Carlo simulation na 1 over root n. Equate ko lang yan. Alright? And this gives us d equals a. That means kapag ang dimension ng problem, mas advisable na gumamit, pag mas mataas yung dimension ng problem, mas advisable na gumamit ng Monte Carlo simulation. Because with the same number of points or of subdivision points or data points na gagamitin sa Monte Carlo, kasing bilis na siya nung composite Simpson's rule kapag ka ang dimension mo na ay 8 or higher. Okay? So actually starting at 8 upwards, mas maganda na yung gamitin yung Monte Carlo simulation than the composite Simpson's rule. Okay? Now, but in practice, we already accept Monte Carlo simulation to be the best quadrature rule to use whenever the dimension of our integral is 6, is at least 6. All right? Pero sa lower dimensions, napakabagal ng convergence ng Monte Carlo simulation. All right? Well, how do we compensate with that very slow convergence? We set n to be large enough in the first place. All right? So yung 1 over root n, siya yung nagdedetermine ng error dun sa Monte Carlo simulation. Now, it might not be as good as the approximates we'll get if we will use composite Newton Cotes quadrature rules or even Gaussian quadrature rules. Pero we can compensate for that in lower dimensions by setting capital N to be large in the first place. So instead of, say, sa Simpson's rule, kung gagamit ka ng 4 na points, you might get good results. Pero don't try using Monte Carlo simulation using only 4 points in one dimension. Kasi napakabagal ng order of convergence. Imagine kung gagamit ka lang ng 4 na points, yung error constant mo ay 1/2 kagad. So it's 50% times another constant. Napakalaki kagad ng error. So to compensate for the spectacularly slow convergence of Monte Carlo simulation, we can choose capital N to be large enough in the beginning. Because as you will see sa susunod nating part ng discussion, madali naman siyang i-implement. We can even afford millions of data points to be used for a one-dimensional integral. Okay? So ano ba yung proseso sa Monte Carlo simulation? Well, simple lang siya. So halimbawa sa one dimension muna tayo. So mag-integrate tayo ng isang function capital F. Yan nga lang yun yung requirement dito. Dapat alam mo yung function na ini-integrate mo or may access ka sa data points o dun sa function values na i-approximate mo with a large number of samples. So dapat marami kang alam na function values or alam mo dapat yung function para ma-compute natin yung function values na kailangan natin. Alright? Tapos ang susunod na ang unang step, we will randomly choose capital N abscissas. X1, X2 hanggang X capital N over the integration interval. Okay? Typo, interval yan dapat. Okay? Now, and then we will calculate the areas of the rectangles form of width B minus A and height F of X sabay. So, pipili tayo, magdodraw tayo, random drawing ng mga X sabays. Kukunin natin yung function value ng mga X sabays na yon. And then itong mga exabytes na to magbibigay sa atin ng function values. When I multiply the function value f of x sub I by the width of the interval given, that's b minus a, I will get the area of a rectangle. All right. And remember from Math 36, you learned that areas of rectangles or summations thereof are approximations to the Riemann integral. All right. So ibig sabihin, yung area ng rectangle na yon, yun yung magsiserve as my approximate for the integral, right? I will do this for all of the exabytes. So I will have several rectangles of different heights, but of the same widths. Pare-paras yung width nila, b minus a. Iba-iba yung heights kasi yung mga function values ay ine-evaluate natin sa mga random exabytes na nabunot natin kanina. Tapos, sabi ng central limit theorems, pag nag-draw ka ng napakaraming data points, pag kinuha mo yung average nila, ibibigay niya sa yung average height of the rectangles, and that average height multiplied by b minus a should be close to the actual value of the integral, which in this case can be interpreted as the area of the shaded region. Okay? Kaya pag gumamit ka ng isang point lamang, isang exabyte, for sure, hindi pala for sure, malamang magiging pangit yung result ng approximation. But if you use hundreds of thousands, tapos in-average out mo sila, posible maging maganda na makukuha mong approximation. Okay? So to understand this process even more, let's consider a specific example. Halimbawa, kunin natin tong integral ng 1 over x squared plus 1 dx from 0 to 1. Ang exact value niya ay pi over 4. And then pi over 4 being the integral, or the value of the definite integral, is actually the area of the shaded region in blue in this figure. Okay? So yan yung gusto nating area na i-approximate. And then nung pinaprepare ko yung worksheet, itong module, nag-draw ako ng 5 random numbers. Unang draw ko from 0 to 1, ang nakuha ko ay 0.506190. Yan yung unang random number. Tapos, pag kinuha ko yung function value niya, nakuha ko ito. And then, I'll form the rectangle whose height is the function value at 0.506190. And then my estimate for the blue area here is this orange portion. And then clearly you will see that this will not, maybe this will not give me the exact area because I have an underestimate here, hindi ko to nabilang. Pero I have an overestimate here, nabilang ko siya na hindi naman dapat siya nabilang. At least visually, it looks like this guy and this guy are off the same area, so I can say that they will sort of cancel each other out. So probably the area of the orange box here, or the orange rectangle here, is close to the area of the blue region we want to estimate. So that would have been a good approximate. But what if your draw is something like what I drew in my second experiment? Ang nabunot ko naman sa as my second random abscissa ay 0.945600. Ito yung function value niya. Ito yung rectangle na nakuha ko. Imagine this being my approximate to the blue area. Mapangit, di ba? Kasi ang laki nung underestimate. I wasn't able to account for this area, which is basically a good portion na nung blue area na gusto ko yung approximate. So this is a miss compared to the first one, which is a hit. Okay? So kaya lang, pag hindi mo alam yung eksaktong value ng integral, there's no way you know when you hit it or when you miss it. So ang idea ay bumunot ka ng napakaraming exabytes. Computein mo yung function values nila, kunin mo yung area ng mga rectangles na yon, tapos i-average natin sila. Okay? So kaya bumunot pa ako ng x3, x4, at saka x5. Nalaman ko lang na hit yung approximate sa x1 kasi alam ko yung eksaktong area na gusto kong i-approximate. Pero usually, in the real world, you will not have any idea of what you are approximating. All right? So wala kang comparison ng relative error. So the law of, we will just rely on the law of large numbers that guarantees us that the more number of instances of the experiment we perform, dapat mas maganda yung approximate na makukuha natin. Okay, so I think I enumerated some of the results there. So dun sa unang draw, okay, parang nilagay ko ba siya dito? Okay, in the first draw, ito yung nakuha ko. Alright, 0.796034, which I guess is a good estimate for pi over 4. Okay. Tapos, syempre, hindi ako sure kung maganda nga ba yan or hindi kasi theoretically, I wouldn't have any idea of what the actual value is. Kaya ginawa ko pa yung second draw, third draw, fourth draw, and so on. So, gumamit lang ako ng 5 draws. Tapos, ang estimate na nakuha ko ay 0.754291, which is about 3.96% accurate. So, posibleng okay na siya for some applications. Usually, for instance, in engineering, we're happy with about 5 plus we're happy with plus or minus 5 to 10% error, all right? Sa math, medyo hindi. Gusto natin 10 to the minus 6, 10 to the minus 8 yung error. But usually it's fine. But imagine this is only 5 draws and the simulation was finished after a blink of an eye. So posibleng gawin natin to hundreds of thousands of times, get the average, and we should get a better approximate. Okay. Now, I performed this with a more number of points. So, halimbawa, okay. Nagdagdag ako ng, ilan ba yung dinagdag ko? Okay. So, nagdagdag ako ng 95 pa na simulations. So, yung limang pinakita ko kanina, 3.96% yung results. Magdadagdag ako ng 95 pa for a total of 100 points used. Using that, those random samples that I got a 1.60% error. So, which is almost, or actually more than half of, more than half improvement from the previous result. Okay. Tapos kung makikita nyo, sa figure 2, yung mga orange dots dyan, that represents the excess that I drew over the interval 0 to 1. Kinompute ko yung function value sa bawat isang dotted line na yan. Kinuha ko yung area, b minus a times the function value. So meron akong 100 rectangles. In-average ko yung areas nila. The average is within 1.60% of the actual area that we wanted to estimate. Okay. Of course, you can further increase your sampling or your sample points. Okay, pwede nyo pa siyang padamihin. So I have 100. I added 150 more. The error was down to less than 1%. Okay, the relative error, I mean. Tapos gumamit pa ako ng 500, 100, 1,000, 5,000, hanggang 20,000. Sa 20,000 draws, bumaba na yung error sa 10 to the minus 4. And it didn't take too long to perform these simulations kasi nga mabilisan lang to. The draw ng 20,000 points, computein yung function values nung data points na yon, all right? Computein yung area ng rectangles para sa 20,000 points na yon. Kunin yung average nila, I'll get an estimate for the actual integral. Okay? Now, in general, so napaka-simple ng idea. Mag-perform ka lang ng maraming simulations, areas ng rectangles, tapos i-average mo sila. Okay? Now, again, we have an idea of how accurate it is. The error will be proportional to 1 over square root of n. Large dimensions, you want to start with a very large value of capital N. Kasi nga napakabagal ng convergence ng Monte Carlo simulations. So formally, the method looks this way. So if you want to approximate the integral I of f of capital X d capital X over a region omega, which is a subset of r to the d. So nag-work siya kahit sa integrals sa multiple dimensions. So posibleng si capital X ay 2, 3, 4, or 5 more variables, all right? Tapos si omega ay isang subset ng r to the 5th or even larger, okay? So ito yung ipa-perform natin. So number 1 is select the value of n, keeping in mind that the error that we get will be proportional to 1 over root n. But whenever you can afford it, you can overstretch. Pwede nyo palakin pa si n than what you expect to be the error. Kasi nga ang Monte Carlo ay hit or miss method. So palakihin nyo na si n, especially for small dimensions. Okay? Because the greater the value of n, the better the approximation we will get, sabi ng central limit theorem on a loss of large numbers. Okay? And then, pag nakapag-decide ka na ilang points yung gagamitin mo, mag-draw ka na ng mga sample points. Pumili ka na randomly ng mga exabytes doon sa set omega mo. Alright? And they should be independent observations of a random variable. Dapat uniform distributed yung random numbers na pipiliin mo all over omega. Okay? Tapos, pag nakadraw ka na, kunin mo yung function values. Alright? Kunin mo yung average ng mga function values, alright, times the volume or the size of omega. So in this way, ito yung function values. Supposedly, siya ay magiging area, no? Or magiging average ng mga areas. So one dimension, ang nangyari ay kinukuha natin yung function value, right? Times b minus a. Kinukuha natin yung summation I going from 1 to capital N. Tapos dinidivide ko siya by capital N para makuha yung average. So ito yung area ng isang rectangle. Isasum ko yung area ng lahat ng mga rectangles na randomly select natin. Kunin ko yung average kaya may 1 over n sa labas. Okay? So ayan yung nagiging estimate natin para sa integral in one dimensions. Pero kapag tapos pwede kong i-factor out yung b minus a kasi constant lang naman siya. Pwede ko siyang ilagay dito sa taas. Right? So kaya ang formula niya ay b minus a over capital N times the summation of the random function values that we draw or that we got. Alright? Kapag ka nasa mas malaking dimensions ka na, yung integration set natin ay hindi na lang isang interval AB. Alright? Sa 2D, magiging rectangle na siya. Or magiging subset na siya ng R2. Sa 3 dimensions, magiging subset na siya ng R3. Kailangan mo lang gawin ay kunin yung area ng integration interval omega. Alright? Sa 1 dimension, ang area ni omega ay b minus a lamang kasi ang integration natin is to be done on an interval. And the size of an interval is its length, b minus a. Kung nasa 2 dimensions na tayo, ang ating integration interval most likely would be a rectangle. So kunin mo yung area ng rectangle, i-multiply mo sa average ng mga function values, that will be your 2-dimensional integral. In 3 dimensions, that will be the volume of omega. All right? So in general, papalitan mo lang yung b minus a by the size of the set omega. Okay? In general, ang tawag natin kay v ay volume. So sa 1 dimension, dahil ang integration set lang natin ay isang interval, length lang siya ng interval. So sa 2 dimensions, kukunin mo lang yung area ng integration surface. Okay? Kaya si V ay magiging area lamang. For 3 or higher dimensions, siya na yung nagiging volume. And that's it. That's Monte Carlo simulation. Tingin lang tayo ng quick examples. All right? Now, magpapauna na ako. I will take probably some more minutes. So if you guys need to attend a class at 12:30 or you have something else to do, then feel free to leave the meeting. And then tatapusin ko lang siya kahit walang matira sa inyo. Tutuloy ko lang yung discussion, mag-monologue ako dito. Pero itutuloy ko yung recording so that you can go back later and watch the recording to prepare you for Monday. Okay? Para matapos ko lang to without calling for another meeting. All right? So yeah, don't worry. I don't expect you to stay, but I expect you to watch the recording nung hindi nyo mapapanood today. But feel free to stay if you have nothing else to do until probably 1 p.m. I can use some company here. Also, you can raise your questions if you have if you seek some clarifications right away. Okay. So let's look at example 1. Here we consider the function x sine x cubed, which is a very wiggly function. Ito yung itsura ng graph niya over the interval 0 to 4. And suppose we want to estimate the integral of f over the integral 0 to 4. Then I computed the actual value here. I guess I used, did I use integration by parts here? Or some other advanced method? Basta, I know that the integral has this exact value. Non-terminating yung decimal, so in-express ko lang siya dito using its first few decimal digits. Okay, pero para magka-idea tayo kung ano yung relative error. Okay. First experiment, I used 100 points. Okay? 100 points lang yung pinili ko sa interval 0-4. Of course, I did a random number. I generated the set of random numbers from 0 to 4. If you're using MATLAB, meron siyang rand command, okay, na magbibigay sa'yo ng isang number from 0 to 1. Okay, so yun yung random number generator ni MATLAB. Isa lang yung binibigay niya na random number. Or if you say random number 1, comma say 100, okay, this will give me kay MATLAB, so kay MATLAB, this will give me a vector, a 1 by 100 vector. So isa siyang row vector with one row and 100 columns consisting of uniformly drawn random numbers from 0 to 1. Okay? So yan yung i-call ko. Kung kailangan ko ng 100 random numbers from 0 to 1 that is uniformly distributed, tapos i-arrange ko siya in a single row, pwede kong ipatawag kay MATLAB rand of 1, 100. Number of rows, number of columns. Alright? So meron akong 100 random numbers. Ang problema ko, ito ay between 0 and 1. Okay? Pero ang integration interval natin ay 0 to 4. So kung gusto mong kumuha ng isang random number between A and B, ang pwede mong gawing call sign kay MATLAB ay A. Ito yung lower limit ng integral. Alright? Plus the length of the interval. So that's going to be B minus A times the random number. Okay? So lower limit plus the length of the interval times the random number. And so this will give us a set of 100 random numbers from A to B. So ganun ko na-generate yung mga data na yun. So nag-decide ako 100 sample points. Tapos nagpa-draw ako kay MATLAB ng 100 random numbers from 0 to 4 that is uniformly distributed. Ito yung binigay sa akin ni MATLAB. Okay? Yung mga orange dots dyan, sila yung 100 points na napili niya randomly. And you see, kind of medyo pangit yung distribution kasi medyo kumpul-kumpul dito yung data points. Where in fact, I expect to have more troubles here at the very oscillatory part of the interval. So feeling ko medyo minalas ako dun sa first draw o dito sa draw ko ng 100 sample points na to kasi nga tingnan nyo, medyo hindi ko na-capture yung oscillatory behavior nung function doon sa buong interval 0 to 4. But I cannot do anything about that kasi in reality, I might not have any way to know how the graph looks like. So yun yung magiging problema natin. Pero here, luckily, I am not expecting a very good approximate kasi nga napaka-focus ng mga data points na napili o nabunot ni MATLAB for me doon sa non-oscillatory part ng interval. Okay? So if I apply this formula, okay, kasi na yung formula natin. Itong formula na to, so size of the integration region, ang integration region lang natin ay 0 to 4. So it's going to be 4 over 100 times the summation of the function values dun sa 100 points na nabunot ni MATLAB. And what it gave me is this, 1.0171 and so on. Tapos napakalaki ng relative error. Kasi alam nga natin yung function value ay ito. Ito yung gusto nating i-compute. Pero ang binigay ni MATLAB, binigay ng Monte Carlo simulation ko ay 1.0 something, which is 284% erroneous. Napakalaki ng relative error. But I expect this to kind of happen because I only used 100 points. So kaya lang medyo pangit pa rin kasi in-expect ko 1 over root of 100, dapat around 1 over 10 or a multiple of 1 over 10 yung error na makukuha ko. Pero malas yung bunot ko. So nagkaroon ako ng misses. So kaya yung relative error ay napakalaki. So that's a problem with a very oscillatory interval. Okay. The second experiment I did is to use 25,000 points instead of 100 points. So 25,000 na yung ginamit ko. Tapos ang estimate na nakuha ko ay ito, 0.42. Ang error niya na lang bumaba na to 17.68%. Okay? You might be thinking superficially that the number of points here are is greatly increased from 100 to 25,000 pero yung computational time was not significantly different. So within seconds, tapos pa rin naman yung simulation. Kahit na mas marami yung points na ginamit ko. Right? And then kung hindi pa ako dyan kumbinsido at marami pa naman akong time, pwede pa akong magdagdag ng Monte Carlo simulations. Okay? Now, posibleng pwede ka magdagdag ng points. Pero typically, sa Monte Carlo simulations, hindi na natin sinisave yung mga data points na ginagamit natin. Kasi imagine, gumamit ka ng 100 million data points. Tapos, gagawin mo lang, usually hindi natin ini-store yung mga function values na kinocompute niya. Kasi kung i-store ko siya, kakain yun ng memory sa computer. So ayoko na kumain siya ng memory sa computer, tapos kakain din siya ng RAM kasi kailangan siyang i-store ni MATLAB dun sa memory ng computer mo na meron siyang instant access. So kung ang RAM ng computer mo ay say 8 gig lamang, posibleng kulang na yon para sa pag-store ng 100 million data points, okay? Tapos kakain din yon ng oras sa actual CPU time sa machine implementation kasi gagawa siya ng read and write process. So magdodraw siya, gagawin niya yung math, tapos isi-save pa niya yung data na nakuha niya. Yun yung nagpapatagal kadalasan sa mga programs. Yung pag-save ng data either sa physical memory, dun sa hard drive, o dun sa RAM ng computer. Usually, hindi natin ini-store yung mga draws natin. So kung hindi pa kumbinsido, ang pwede mong gawin ay ulitin mo na lang yung experiment. Mag-draw ka uli ng 25,000 random sample points, kunin mo yung average ng mga function values, i-multiply mo by the size V of your integration interval, then you will get another estimate. Ginawa ko siya dito, dun sa third problem, nag-redraw ako ng 25,000 more sample points. So ito yung result natin kanina sa unang draw. Pangalawang round, bumunot ulit ako ng 25,000 sample points. Ginawa ko uli yung estimation process. Ang nakuha ko naman ay ito, si I2. Tapos ang error ay 5%. Ginawa ko siya third time, 25,000 points. And I get an estimate with error 6.68%. You see that ito yung probabilistic nature niya. Same number of points used, pero dahil randomly generated yung mga exabytes, iba-iba yung mga estimates na nakukuha ko. Right? Some of them are good hits, some of them are bad misses. Alright? Tingnan nyo to, 17%. Pero yun pala, pwede ako maka 5%. Pwede ako maka 6% lamang. Tapos, pwede nga less than 1% kung medyo sinwerte ako ng bunot. Alright? Tapos, kunwari, hindi natin alam na ito yung mga relative errors, so we cannot decide which of these values are good enough. Pwede ko na naman ako mag-appeal sa central limit theorem na, okay, marami na akong experiments na ginawa, marami na akong data points na ginamit, perhaps I can average the results of several Monte Carlo simulations. Pwede kong kunin yung average ni I1 hanggang I5 and I will consider that to be my estimate I sub ave. So tapos ito yung i-report ko na estimate ko dun sa integral. Alright? Which is on the safer side kasi 1.58% error siya. It's not as good as I5, pero kung hindi mo alam yung actual value na ina-approximate mo, which is understandable sa actual experimentation or sa actual research phase. So wala kang choice kundi gamitan yung mag-appeal sa central limit theorem na kunin yung average na lang ng several simulations na ginagawa mo. Alright? So it's as if you use 25,000 times 5 data points to generate this estimate. Okay? So ito yung parang, ano bang pwede natin itong tawagin? Pwede siguro natin itong tawagin, hindi ko alam kung ano yung technical term. Pero para siyang grouped Monte Carlo simulation na sa bawat run, gumamit ka ng 25,000 points, tapos kinuha mo na lang yung average ng mga estimates among several parallel lines ng Monte Carlo, parallel runs ng Monte Carlo simulation. So lalo na ito kung maraming cores yung computer nyo, halimbawa ang computer nyo ay 16 gig na RAM, tapos halimbawa, meron siyang 8 cores. So, pwede kang mag-parallel computing, yung pwede mo ipagawa sa 8 CPU o 8 cores ng CPU mo, tigi-tigi sa Monte Carlo simulation, so nag-run sila at the same time. So, sa isang pasada, nakaka-perform ka ng 8 Monte Carlo simulation, say with 25,000 sample points each. Iba-iba yung approximate na manggagaling dun sa different parts ng CPU mo. Kunin mo yung average nila that is more likely to give you a better approximate than any one of those 8 batches. So, parang ganun yung pwede nyo gawin. And um, hopefully, hindi ko pala alam kung saan natuturo or kung natuturo ba sa atin kung paano gumamit ng parallel cores. About 12 cores yung computer mo, 16 cores, or kung yung iba sa inyo marunong ng GPU, paggamit ng GPU, yung kagandahan ngayon, no, yung mga gaming laptops, hindi na lang siya para sa gaming talaga, mataas yung specs, mataas yung GPU. Yung GPU ngayon, pwede nang gamitin ni MATLAB para mag-compute. So, i-close nyo muna si Dota, i-close nyo muna si LOL, ano pa ba nilalaro nyo ngayon na RPGs. Close nyo muna siya, wag muna kayo maglaro, gamitin nyo yung GPU para mag-perform ng parallel Monte Carlo simulations para makakuha ng better approximate. So that's one way on how to improve your Monte Carlo simulation. Well, there's another way, especially if you have an idea of how your function looks like. Katulad nito, alam natin na yung function natin ay napaka-oscillatory. Okay? Pwede kong gawing stratified yung pag-compute ng random numbers. Okay? Now, dito sa example number 4, ang ginawa ko ay kalahati nung 100 data points. So 100 data points yung ginamit ko. Kalahati sa kanila ay finorce ko to be on the interval 0 to 2. Tapos yung kalahati, finorce ko to be on the interval 2 to 4. Kasi ito yung naging problema ng example number 1 natin. Masyadong nag-concentrate yung mga nabunot kong data points or exabytes doon sa interval 0 to 1 wherein there's little action happening. Alright? Kakaunti yung points na nakuha ko dito sa oscillating part. So kung alam niyo yung itsura ng function, pwede kayong mag-stratified Monte Carlo simulation or pwede niyo siyang isipin as composite Monte Carlo simulation in the sense that you will devote half of your data points from 0 to 2 and force the other half to belong to the interval 0 to 4. And then you get your estimate using the usual Monte Carlo formula. And in my case, I got an estimate which is about 46.75% error. Medyo malaki pa rin, hindi pala medyo, malaki pa rin talaga yung error. Pero at least it greatly improved. Remember from before, it's about 284% if I'm not mistaken. It's now down to 46.75. And probably you guessed what I can do next. Posibleng mag-alat ako ng mas maraming points pa rin dun sa mas oscillating na part. And that's what I did in number 5. Pinili ko lamang ay 100 points from 0 to 2. Tapos yung 24,900 points, pinili ko to be on the oscillatory half of the function. Okay? And here I got a good result of about 4.91%. Okay? Now, ito yung itsura niya. 25,000 points yung ginamit ko. 100 sa kanila ay dito ko pinalagay kay 0 to 2. Tapos yung 24,500 dito ko sila nilagay sa 2 to 4. Tingnan nyo, napaka-dense na nung distribution. So, ibig sabihin, mas nakaka-capture ko rito yung behavior dun sa oscillatory part. Kasi mas maraming points yung pinili ko sa kanya. Alright? But again, Monte Carlo simulation is a hit or miss thing. So, it is always better to start with a very large number of points first rather than redoing the Monte Carlo simulation several times. Okay? Now, before I proceed to the second example, do you guys have any questions so far about the method itself? I think it's simple, but do you have do you want to clarify some things? Or okay lang ba? Clear naman ba yung method? Okay, thank you, Ezekiel. I'll assume that's also the thing for everyone else. Now, tingnan natin yung paano nangyayari pag two-dimensional naman yung integral. Okay? Now, if our function is y sine x minus x cosine y, so function of two variables, so yung omega I over r squared. Tapos halimbawa, gusto kong i-estimate yung yung iterated integral of this form. So I am integrating on the square whose x values are between -5 and 4 and the y values are between -4 and 5. Okay? Ang exact value ay ito. Oops, sorry. Tapos, para malaman natin gaano ka-accurate yung ginagawa nating evaluation. So may apat na tanong dyan. Okay? And let's walk through them one by one. But first, common to all problem is the size of omega. Ano yung volume o size ng integration surface? Now, we are integrating over two intervals. On the y-axis, it would be from -4 to 5. And on the x-axis, it's going to be from -5 to 4. So here, this interval is of length 9. So kung i-drawing yung integration interval, sa y-axis from -4 to 5, tapos x-axis from -5 to 4. Okay? So ito yung integration interval natin. Kukunin natin yung volume yan. Or kasi 2D lang naman yan, so yung area ng integration region. So this is of length 9. This would be of length 9. So the volume is 81. Or the area of the integration region is 81. So let's take note of that. So that's V. And then, tingnan natin yung graph. Okay. Ito yung graph ng function. Y sine x minus x cosine y. So first problem, sabi doon ay gumamit ng 100 points over the integration region. So pinakompute ko lang kay MATLAB, pumili ka ng 100 ordered pairs where the x's come from negative, where are the x's from? Where the x's come from -5 to 4 and the y values are from -4 to 5. So ang pinadraw ko kay MATLAB dito ay 100 ordered pairs. X's belonging from -5 to 4 and y's belonging from -4 to 5. Tapos kinompute ko yung function values, tapos pinlot ko lang sila on a 3D graph together with the function values. Okay? So nangyayari dito ay, kukomputing ko ngayon yung volume na na-generate ng bawat isang function value. Take for instance this function value, right? Titingnan natin ano yung cube na nabubuo ng function value na yon. Remember, si x ay from -5, sorry, lagi ko nakakalimutan. Si x ay from -5 to 4. So from -5 to 4, tapos si y naman ay from -4 to 5, -4 to 5. Okay? Tapos halimbawa, ito yung function value na titingnan ko. Kukunin ko yung volume nitong cube na to, hindi pala cube, itong rectangular prism formed by that function value as the height and the actual integration region omega as the base. So kaya 81 times the function value. Kasi 81 yung area nung base, tapos yung function value siya yung magbibigay sa akin ng height ng rectangular prism. So makukuha ko yung area ng rectangular prism corresponding to that point. And that will serve as my estimate for the integral using 1 point. But again, it's a hit or miss thing. Kaya ang papagawa ko kay Monte Carlo kay MATLAB, pumili ka ng 99 pang points para mas sure ako or mas maganda yung approximation na makuha ko. Kukomputin ko yung area ng mga rectangular prisms using those other 99 function values that we have drawn. I'll take the average of all of these volumes and I will get my estimate for the integral of this nice looking graph over here. Dito sa figure B, pinakita ko lang yung mga X, Y na na-draw ni MATLAB, right? So, kung bibilangin niyo yung blue dots na yan, 100 yung mga yan. So, 100 ordered pairs yung ginamit ko. Alright? Now, the result here is this. I got 7.833, which has relative error of 323.64%. Nagkuripot ako dun sa dun sa number of points na ginamit. So, kaya nga sabi ay wag na kayong magkuripot kung kaya naman ng memory nyo, damihan nyo na kagad si N to begin with. All right? Now, I run this simulation several more times. Tapos, siguro yung pinakamagandang results na nakuha ko after running it 10 times will have relative error of around 18%. Okay? So yon, medyo kuripot ako, 100 points. Pero dun sa second problem, sinabihan na ako na, okay, 100,000 points yung gamitin ko. Tapos mag-perform ako ng 5 Monte Carlo simulations. So, first Monte Carlo simulation, draw 100,000 exabytes, compute the function values, get the area of the rectangular prisms by multiplying the function value by 81, which is the area of omega. Ito yung mga nakuha kong results. Simulation number 1, 2% error. Simulation 2, 16%. Simulation 3, about 9%. Simulation 4, 19%. Simulation 5, 8%. And because I don't know, or kunwari wala akong idea kung ano yung relative errors, ito lang yung nakikita ko after each experiment, the law of large number tells me, okay, siguro mas okay na i-average ko na lang sila kaysa pumili ng isa sa kanila to serve as my estimate. Okay? If I take the average here, nasulat ko nga ba siya? Hindi ko pala kinompute yung average. Bakit hindi ko siya sinulat? But the best one is about 2.10%, and the worst is 19.38%. They are a lot better than the results with just 100 points. Okay, and again, I guess we will have the best of both worlds if we will get the average of these 5. Okay. Sa problem number 3 naman, pinag-run ako ng Monte Carlo simulation ng 1,000 beses. Tapos gumamit ako ng 100,000 points for each run. Okay? Tapos kinuha ko yung average ng mga estimates na yon. Nakuha ko tong number na to, which has error of about 4.59%. Okay? And then I can try to even increase it. And siguro niran ko rin siya for 10 million points. Imagine how many points did I use? Napakalaki ng 10 million. Pag ginawa niyo siya sa Gaussian quadrature rules o ginamit niyo siya sa Newton codes, hindi na kayo matatapos kung gagamit kayo ng 10 million points. Alright? Pero sa Monte Carlo simulations, mabilis lang yan, especially if you have a large number of cores in your computers. Ano ba ang usual ngayon? Usually 4 cores sa mga computer, quad cores sila. So, ibig sabihin, 4 yung CPUs na yan. Pwede yung ipagawa bawat isang simulation sa kanila ng sabay-sabay. So, 4 yung nagtatrabaho at a given time. The first run I got with the 10 million points, ang accuracy niya ay about 2%. Tingnan niyo, mas maganda pa siya mas maganda pa yung nakuha ko using only 100,000 points. But again, it's a hit or miss method. Tapos niran ko pa siya several times. The errors are between 0.5% and 2.89%. All right. Tapos these values are within the ballpark of the estimate when n is equal to 100,000. So, kaya napakabagal nung convergence niya. So, gumamit ako ng 10 million points. Yung relative errors na nakuha ko is around between 0.5% and 2.89%, which is at the same ballpark as the relative errors we got using only 100,000 points. So imagine the leap from 100,000 points to 10 million points, hindi ganoon kalaki yung improvement ng approximate. Kaya napakabagal ng convergence ng Monte Carlo simulations. Right? But it compensates for the easy implementation, and also Kokonti yung computation sa kailangan, hindi naman kokonti. Mas simple yung mga computation sa kailangan natin gawin. Kaya usually, isa ring go-to method ang Monte Carlo simulations. Okay? Now, yeah, and I think that's it. Do you guys have any questions? Meron akong MATLAB code. I don't know if you want to see this. Pero talaga napaka-simple niya lang. And I guess you can write your own program for this. Na-outline ko na naman paano mag-draw ng random numbers. Pag nakapag-draw na kayo ng random numbers, kailangan nyo nang i-implement itong formula na to. Okay. Mag-draw ng random numbers, computein yung function values. Alright. Kunin yung average ng mga function values, tapos i-multiply by the size of omega. Gaano kalaki yung region of integration. And then that's it. That's your estimate. Okay? So, any questions?
Sir, nothing about the subject po. Pero I joined mga kaninang 11:40.
Okay.
And meron kayong sinend na Google Forms dito, sir?
Yes, yeah. Nagsend ako ng Google form kasi 'di ba meron tayong final project for the course which will be due during the first week, during the finals week. So, pwede kayo mag-work kasi with a group of at most 4 members. You can do it alone if you want. You can do it by pair. Pwedeng trio kayo. Pwedeng at most 4 members. Tapos, bahala kayo kung meron kayo naiisip na ka-group, ka-pair, mula sa section nyo or mula sa kabilang section o mula sa kabilang lecture, okay lang din. Pwede kayong bumuo ng sarili nyong group. Next week ko hihingin yung actual groupings. Pero kung gusto nyo mag-work with a group, pero wala kayong idea kung sino yung mga pwede nyong makagroup, pwede kayong magsagot ng Google form na sinend ko dito sa chat. Sinend ko rin siya sa email via Canvas, so check it out. Tapos pakisagutan siya until Thursday next week para malabas ko yung grouping by Friday. So ako na yung mag-group dun sa mga wala pang naiisip na ka-group para hindi naman kayo ma-burden na or ma-force na gumawa mag-isa ng project. The guidelines for the project will be out next week perhaps kasi tapos na yung course. So congratulations guys. Natapos na natin yung lecture for Math 174. So next week we can meet or we can still meet to discuss the details of the project and also to talk about the problem set. I'll give the problem set next week. I just forgot the exact dates. I-check ko na lang dun sa course outline natin. Or probably I can do that today. Dahil nag-overtime na rin naman tayo. Sana may copy ako dito ng course guide o module 1. Tandaan nyo ba guys kung kailan dapat yung final problem set? Let's see. Okay. The final problem set would be next week. So probably I'll give it on Tuesday and it will be due on kailan nyo gusto maging due. So I'll give it on Tuesday. Tuesday ko ibibigay para tapos na kayo ng exercise para hindi siya mag-overlap. So you'll have lab exercise 7 on December 13. Tapos problem set will go live in Canvas on December 14. Tapos kailan nyo yung gusto yung deadline? Gusto nyo ba 17 or 20? Sige na nga ako nang pipili for you. 20? Okay lang ba? December 20 yung deadline yung problem set. So bibigay ko siya Tuesday next week. Okay, thank you, Chazel. Yeah, that's also what I thought. So sa 20 na yung deadline. Or pwede naman sagarin, gawin na nating 21. Okay? So from 14 to 21. Tapos mag-meet pa rin tayo Tuesday next week para pag-usapan yung project. Alright? Tapos na tayo ng modules. So project tayo discussion on December 14th. And then I can also go online on Thursday next week para kung may mga tanong kayo dun sa problem set. Okay? But that will just be more of a consultation thing. Okay? And then, yeah. Siguro may i-require, inisip ko kung Sige, wag na lang. Next week ko na lang sabihan. So yeah, I think that would be our schedule for the rest of the course. Yeah. Other questions? Okay, so if there are none, then thank you guys for sticking around and congratulations, you survived the lecture. Though meron pang tatlong requirements na natitira. Lab exercise 7 on Monday, problem set number 2, which will be due on the 21st, the last day of classes. So ang ganda ng Christmas break nyo na wala na kayo masyadong iisipin aside from meron pala yung final project which will be presented or submitted during the finals week. All right? So yeah, that's it, guys. Thank you for joining me today. Enjoy the rest of your day and also the weekend. It's coming up just a day to go. And let's see each other again on Tuesday. Bye, guys.